See, at the end of class in the chat, there was a question from Omar, should you pick one processor or a different one for each purpose? So for the class, if you're a beginner, by all means pick one, but I use all of them and it varies. So when I need a small process, small size, low cost, low pin count for a simple embedded task, I like the AVRs. When I need fast processing and parallel processing, I like the RP2040. When I need radios, I like the ESPs. There's a Venn diagram of how those overlap. Let's see, when I need embedded USB, I like the SAMDs. So there's a good use case for each of them. So I end up using all of them. If you're a beginner to start, you can pick one and focus on it.
Perfect. Thank you, Neil. Thank you.
Yep. So from there, this week is scanning and printing. And then we do have a recitation on the 24th. That's going to be about AI. And we're going to split that in two parts. In part, it's going to be AI for design. And then the other part is going to be AI for embedded processing and programming and inference. So important recitation coming. Then also a note, I see many cameras off. When we're in class, we expect your camera to be on. We want to see, not just me as a we, but we want everybody to see everybody. The body language in the class is very important. So, how you're reacting, what's going on, your lab context is part of the process. That the nonverbal communication goes with the verbal. So there's too many cameras off. When we're in class, your camera should be on. I want to see you as well as you seeing me. Just what I'm looking at now, Matthias, Shivraj, Bir, Shoko, Thangam, Shima, Miko, Ho, Sangai, Lean, Andy. Your cameras should be on. And with that, we'll start in on this week. So this week is scanning and printing. From the outset, you might have viewed this as a 3D printing class. You're going to learn about the strengths of 3D printing, but also the weaknesses. And in the coming weeks, you're going to meet alternatives to 3D printing. Embrace 3D printing, but also look beyond it. This is an article on the birth of subtractive machining that began, you can trace with a somewhat complex history to MIT in 1952. This isn't one article on the birth of 3D printing. And there's maybe 3 different claims to the birth of 3D printing in America and in France. But the crucial, oops, I closed that. The crucial distinction, of course, is in 3D printing, you add rather than remove material. So here's a few examples. This is a really interesting Swiss designer who 3D prints clocks. This is a project making microscopes that are all 3D printed. You'll meet this project when we get to machine building. This is an almost all 3D printed little milling machine for making circuit boards. So one good thing about 3D printing is complexity. that it takes the same time to make a complex geometry as to make a simple shape. So complexity is cheap. One is access. If you wanted to make an axle that goes through um, uh, a car, for example, subtractively, you would have to make them separately, attach them, and assemble them. With 3D printing, as you're printing, you have access to the interior as well as the exterior, so you can make completely nested parts that you couldn't otherwise get to. It's largely net shape, which means material goes where you want it. You don't have to remove material where you want it. And ideally, there's very little waste from 3D printing. So those are the benefits. However, it has many constraints. So yeah, Benchy is a popular test for 3D printing. One of the problems with it is 3D prints can fail. So if you're extruding, you can make spaghetti, is the term of art for it. It doesn't stick together. Um, uh, this has happened to me. I was running a 3D printer in a fairly cold room, and the nozzle plugged, and it was a long print job. And yeah, 3D printers can be left unsupervised, unlike lasers. And when I came back, the nozzle had plugged, and it was just sort of extruding out the top of the nozzle, disassembling the machine. These are powder printers that can have earthquakes. Resin printers can make goo. So one constraint is you can fail. One is resolution. You're limited to the size you extrude. And so depending on your printer and milling machine, you can mill much finer surfaces finishes than you can um, print. One is time. So there's been a contest to see who can print the fastest benchy. Um, let's see. This is a video that's not playing. Or let's see, maybe this is a link to it. So there's an extreme of, let's see, if of optimizing printers specifically for the job of racing to win the benchy contest. And so you'll have to play the video locally to see it. I'll put that in the chat. These races to print a benchy in a few minutes, and it's generally a pretty terrible print. And most anything you want to do that's non-trivial can take hours, and it can go up to days. Another limitation is the open materials are quite affordable, but the more advanced printers use proprietary materials that can be very expensive. And then these are links. These are two good links. This is Prusa's material map. Here's another material map. There's a subset of materials you can print. We'll see. Let's see. Yanni is noting about uh, fires for leaving it alone overnight. Um, so there are flexible materials, there's translucent materials, there's rigid materials, but there are limits. There aren't very hard materials you can print. There aren't very very transparent materials. There aren't good electrical conductors. So other processes we're going to cover can actually there's this typical 3D printers can't do food. I'll mention food in a little bit. So there's a range of materials you can't 3D print will do in other processes. So for polymers, uh, polylactic acid is by far most common. polylactic acid is great. It's plant-based, so it's renewable. There's very low volatiles and particles, which I'll talk about. It's easy to print. The prints are somewhat brittle. Um, PETG is not plant-based. It's non-renewable. It's oil-based, but it is recyclable. It's a little bit harder to print, but not much, and it's tougher and it has good UV resistance. So PLA and PETG are good starting materials. Then there's a wide range after that: PMMA, ABS, HIPS, TPU, PVA. These are used for things like flexibility or solubility. Um, you can get what's called metal, but the metal is a composite you extrude and then you have to fire. And then wood is not pure wood, but you can get wood polymers with wood fibers that make nice wood-like parts. Um, then these materials generally are hygroscopic, which means they absorb moisture. So you need to store them so that they are sealed from the environment. It degrades over time. You can try to cook it that improves it, but you need to be mindful of how you store your filament. If you just leave it out for a long time, the moisture it absorbs will degrade the print quality. Um, let's see, let me move that link. When you print, all told, there's about 100 parameters you need to set. Uh, I'll add a link to this. This was a project in my lab developing a 3D printer that can adaptively learn to print material. The printer itself is full of instrumentation, and so while it prints, it studies the material and learns how to print it. But in general, and that's aimed to expand use of recycled and renewable material. There's a lot of settings for any material. For most of the materials you're going to use, um, there's preset settings. See, Garrett is asking on updates. Garrett, there's incremental updates. Jake has, he's now working on combining the slicer with the printer. So the path planning knows about the printer to adapt. And then beginning work looking at things like screw extruders and extending it to machining. And then this link is to a really nice article that was co-written by a research scientist in my lab on the life cycle. And what they're studying here is sustainable sourcing of these polymers. So they come from plants, but then a life cycle so that the end of life, instead of throwing this away, you can use that to feed the plants again. So trying to make a closed life cycle for biopolymers for printing. And so this was a good collaboration studying sustainable biomaterials. Now, here comes a really important point for today. This article is about what gets emitted by the printers, and there's a couple important graphs here. So this is studying ultrafine particles. Ultrafine particles are exactly what is the concern with like bad air pollution days. This is a logarithmic scale. These are powers of 10. So this is a huge range. What you'll see is PLA is down here. That's fine. These other materials emit a lot of ultrafine particles. And this is just like, it's not just like, it is air pollution. So a PLA printer you can use, or a PETG, you can use in the open with nothing special, like the one behind me. Anything beyond that, you either need, well, first, before I finish that sentence, the other thing this article is showing is these are volatile organics. And so this is like, breathing next to a chemical factory. Again, PLA is fine. Many of these other materials are very high volatiles. So for these, either you need to use those away from people in a ventilated space, or you need to use them in a sealed printer with what's called a HEPA filter that filters what comes out from it. But it's very important to be aware that open 3D printers in an office environment, you need to stick to the low volatile materials. Again, PLA and PETG. Anything beyond that, you need filtering or ventilation. And this is an article from Prusa on their certification of printing with their printers. And they talk through the materials that pass and the ones that don't. So these are not safe. You need to be cautious about the fumes coming from them, depending on what you're printing. So then comes design rules. And I'm going to talk about food safe in a little bit. Um, let's see, let me remember yeah, okay, I'm going to talk about food safety in a little bit. So design rules are what separates beginner from more advanced 3D printing. So the first one is supports in the printer. And the most impressive example of that is this was a project using a laser fusion printer that I'll talk about. And it was to print a shirt. And what they're doing mathematically is dropping the shirt into a volume. This is the print volume you're going to print. Making sure everything isn't quite touching, and then sending that to the printer. And so when you print that, you need to support all of those overhangs. So in this list, these are FreeCAD files, JPEG images, and STL files. So this is just an overhang. So if you have a part that sticks out like that on a one material printer, what you do is you print a second material and you have a slight gap, and then you have to reach in and pull that out. Then here what I'm testing is these are a series of parts getting a smaller and smaller clearance, and these are in fractions of a millimeter. And all of these released, but when the gap got that small, that was too small and those didn't release. So the next design rule is how close a part can be and not bind. Then ideally you want to print without supports. So this was an extreme form. This was a student originally in this class who studied how to modulate, how if you slow the printer down so not enough material is coming out, it sort of burps and it makes fabric. He's not speeding it up and slowing it down. He's just not giving it enough material and he's tuning it. And then he used that to make beautiful fabric. And then he did a crazy print job. So here he ran printer for a month, just going around and around and around. And um, he makes this fabric that was as big as one of the sports fields at MIT. So all of that's done without supports. So this is one of the most important lesson. Patrick, yeah, these are fine for the group assignment. Um, this is one of the most important lessons from today. Straight up builds just fine. If you go straight out without supports, you get spaghetti underneath. But if you look at the angle, when you get to about 30 degrees, each layer can build on the next layer. So a 30-degree angle, you can print without supports. And so if you use that as a design rule and you don't have flatter angles than that, you don't need supports. Overhang is how far you can go before you run into this. And so when you go far out, it's a mess. But short overhangs don't need supports. And then this is a really important one. Um, if the printer is pulling the filament and there's some tension in it, and so this is called bridging. So this was done without supports. And so if you're building up on one side and you're building up on the other side, if you're pulling between those, you can pull the filament and attach it and then build on top of that. And so bridging works without support. So if you're making a house, like a door or a window, you can print and not support because you can do bridging over it. Um, Wall thickness is how thin you can make something. And I did this on a resin printer, and I'll talk about the different printer types. And so here you can see I'm going down to a very fine wall. But on an extrusion printer, you couldn't make a wall that thin because of the thickness of the extruded filament. So there's a limit to how thin a wall can be. Next is, this is just a test part where I make an inner and an outer diameter. And there's typically quite a few percent difference between the dimensions you ask for and the dimensions you get back from the printer. And so when you're doing precise mechanical design, you need to characterize the printer dimensions versus your dimensions. Typically, the structural properties are anisotropic, meaning they're different in different directions. So on this one, if I pull in that direction, I'm pulling in the direction of the filaments. If I pull in this direction, I'm pulling between the layers, and the layer adhesion is weaker. So it'll fall apart more quickly in this direction than in that direction. Um, the surface finish is a function of angle. So when it's, for example, vertical walls, you don't notice the steps, but at a flat angle, the steps are much more noticeable. Uh, One of the things you need to pick is the infill. So the hollow part is fastest to print, but is weakest. The dense part is slowest to print, but is strongest. And in between, you can vary the density of the fill based on the trading off time for mechanical properties. Uh, and then uh, you want to avoid a sharp corner like that. Because if you have a sharp corner, what you'll get is, say, one pass of the filament and then, maybe two passes. And so when you actually print it, what you'll get at the end is sort of spaghetti. Um, you want to have a face that has enough pass of the filament to give you a good interface. So just in the design rules, you want to avoid sharp corners. When you print, a key parameter is the distance, again, for an extrusion style printer between the head and the bed. If you're too close to the bed, it can't print. There isn't enough room, and eventually you gouge the bed. If you're too far from the bed, you end up just making spaghetti in space. And that's a particular concern if the bed is warped. And so um, current printers all know how to probe the bed to measure curvature and to measure their distance to it. And then they adjust their printing once you've set that setting. Simpler printers don't do that. Those are increasingly almost all current generation printers do know how to do that. Then the next issue is you're printing on the bed, but you need to be able to remove it. So if the adhesion is weak, that's one of the ways you get spaghetti. It just doesn't stick. You'll see mention of, for example, using glue on the bed. I don't like that because it can make it hard to remove and makes a mess. In general, if the bed is clean and is at the right temperature, you'll then get good adhesion. But two other issues. One is if you have a part that has limited contact on the bed, that's not enough to hold it. So you can produce what are called rafts, which is a layer underneath, and brims, which is printing beyond the edge of your part. And those help with adhesion. And then depending on what you're printing, the print temperature can lead to warping in your part. And generally, that's better in a sealed printer that controls the temperature in the chamber to minimize the gradients. Uh, Once you're done, there's a lot you can do. You're not done. One is depending on the printer you're using, you can see the features of the print process. So this is, for example, a coating that's designed to smooth a 3D printed part. And we're going to go back to that when we look at molding and casting. And a nice process you can do is electroplating. You can metallize a 3D printed part in an electroplating bath. And this talks about how to do that. So now we get to printing processes. Shapeways is a service bureau. See if this link is still current. They had some issues as a company. Shapeways failed, but I thought that they came back. I thought somebody bought them. The original business failed, but I believe they were purchased. Okay, so yeah, this is linked not where I had the that original link, but this is the range of materials they're able to print. So if we go through 3D Systems was the original inventor of stereolithography. Stereolithography uses a laser in a bath, and that's generally the highest resolution printing process. Fused deposition molding was invented by Stratasys. That's extruding a polymer. That's a more office-friendly process and has good structural properties. FDM is a term from Stratasys. Fused filament fabrication means the same thing, but it's not a proprietary term. And there's a lot of updates to it. So this is a note on extruders and the move to larger nozzles that let you move more material more quickly. These are colleagues who print all sorts of interesting materials architecturally. This is a colleague who prints concrete to make buildings. direct energy deposition or wire additive is an emerging process where instead of extruding a polymer, you extrude a wire. And for example, a little ring of lasers melt the wire for metal 3D printing. Binder jetting, which came from an MIT colleague and was commercialized by uh, a local company, uh, has a powder bed and prints a binder that sticks it together, and then you post processes it. So, for example, for ceramics or metals, you bind the ceramic or metal, shake off the unused material, and then you bake it in an oven to fuse it. And that's good for all kinds of hard to print materials like metals and ceramics. Um, PolyJet right now is the best multi-material process. This is where you print like an ink printer, but in 3D with a print head that can have multiple materials, multiple colors. Selective laser sintering is unlike binder jet, where you print a binder. In selective laser sintering, um, you use a laser to fuse a powder together. That's a leading metal process. Those systems can cost $1 million. Uh, Two photon is where it's like stereolithography, but you use an optical process that needs two photons rather than one. And while that sounds minor, the difference is two photons means you take the square of the shape of the light distribution that can make it much higher resolution. And so that's used for nanoprinting. Um, let's see, Dorji, are you asking a question? There's a hand raised? No. Okay. Bioprinting is where you extrude biopolymers, and that's increasingly used in biotechnology. And this is an early event at the beginning of digital fabrication, meaning discrete assembly rather than analog 3D printing. And a lot of the current work in my lab picks up on that. So let's look at machines now. RepRap came from a dear colleague, Adrian Boyer, and his goal wasn't simply 3D printing. His goal was to see how much of a printer's parts could be made on the printer. And so um, this is a wonderful article on self-replication and then on the goal of RepRaps making RepRaps. And so um, that was the real inspiration of the RepRap project. RepRap was open source. One of the things that came from it through Fab Lab in the Netherlands was Ultimaker, that started from that design and minimized the moving mass to increase the print speed. And a fun project from there is Joris, who came from the Fab Lab and RepRap, um, was a leader on this project to print an elephant. And so here the printers have a print volume, but they're on gantries. And so the gantry can rise up and then they pull the parts out. And over the course of about a month, um, they made let's see, let's jump ahead. They made an elephant. Oh, and by the way, this is an example of why I complain about YouTube videos breaking. Why we want your videos in the repo. Let's see, Patrick is putting a link to this family tree. Oh, nice. Um, so if we
So
continue,
if you
go
go
ahead.
to the previous page and just below, you have the whole family tree.
Here.
Just below. Yeah.
Ah, okay. Oh, that's great. I didn't see it. Oh, Oh, that's great. I'll link that. Okay, so Ultimaker. Then Prusa, uh, Prusa has done something really interesting, which is they hardened the mechanical engineering. They make a family of machines, and what Prusa does that's incredible is wonderful is you can buy the machine, you can buy a kit, but all the designs are open. And so it's completely open source, but they built a business around that. And so here's all those parts, made on a Prusa. One of their interesting machines, which is behind me, is the XL, which is one reason to print with multiple materials is just color. So here I'm printing with two different color materials to have things like text in your print. But another reason is you can print a soluble material, you can print a flexible material, and the many of the other machines have one head, and you have to feed the material in and out. What I like so much about the XL is it has multiple print heads. So all the print heads are set up with their material, and it robotically takes the heads in and out. And so it's much more efficient for multi-material printing. That's what I recommend for that. And in fact, Prusa goes further, and they have a whole automated factory system to run these. And so Prusa's factory makes many of the Prusa parts on their own printers, descending from the motivation of the rep wrap. And they have impressive automation for that. Then SaneSmart and Bamboo worked on cost reducing, designing for manufacturing. Bamboo came out of drone engineers with sorry, if we go back, so Bamboo has a nice multi-material feeding printer. It's sealed, it's HEPA filtered, it has a vision system, it automates everything. So this is multicolor printing with that. The one, and let's see, yeah, these are doing the design rules on the Bamboo. I'd say the Bamboo is nice because everything is automated. On the other hand, it's harder to change things. It's harder to adapt parts. You can have filament breakages that are inside that are hard to clear. The Prusas, for example, are more easy to experiment with changing materials and settings. So then Formlabs was started by a group of students from my lab. Oh, actually, let me fix that link. So they have stereolithography printers. I was linking to the 3. The 4 is the most common one. And so with that, these are the test parts made on the resin printer. And again, if you look at, for example, this, you can see it's much higher resolution. With the current printer, it's about, let's see, with the extrusion printers, about 10 mil, 10 thousandths of an inch. A mil is 25 microns. With the resin printers, they're getting down to about 50 or 25 microns. This was let's see, there was a fight between them and 3D Systems that ended up getting settled in part when we put them next to each other in my lab. This is a nice story about that. This is a movie, a stop motion movie made on it that's spectacular. This is every frame in this movie was a different 3D print. And this was a competition they did between, this was mass customization, making custom characters you can order. Then they also make a laser sinner process that's not metal but nylon, but that makes it not $1 million but tens of thousands of dollars. And with this, these are the parts with it, and in particular, the unfused powder supports the fused powder, and so you can make much more complex geometries. Then Stratasys, again, so this J55 printer, it inkjet prints polymers. And so this one by far does the best right now in multi-material and color. These were all printed with no post-processing on this printer. This printer, however, costs as much as a Fab Lab. It's about $100,000, and it's proprietary materials. But right now, this is the winner for multicolor printing. So then there's a number of open source machines, like in machines from Danielle and Gracia. Hang Printer is a really interesting open printer where instead of a fixed gantry, you have a moving print head that lets you print large things in a 3D space. E3D is an aftermarket company that makes hot ends, extruders, all sorts of ways to improve your printer performance. And then we already mentioned Precious Plastic. They make materials that let you make your recycled materials. And then another one is Philistruder. Lets you make your extruders that let you make your own custom materials. So then to buy these, there's a number of vendors. So Protopasta is one, Matter Hackers is one, that sell a range of these filaments. So the metal-looking ones, the wood-looking ones. These have really proliferated. Again, be aware that the more advanced ones need good ventilation. They can also be much more abrasive on your printer. But there's been a tremendous proliferation of these sources of filaments. Then 3D printing works great onto fabric. These are a few different articles on you can combine 3D printing with fabric to print on it. Now we get to food, and here are 3 different links. So there's this is Farm Labs on food safety. This is Prusa on food safety. This is a Hackaday study on it. There's 2 issues. One is it's like being kosher. All the materials need to be food safe. So you have to make sure the printer never printed materials that weren't food safe. And then the other thing that's just that the materials themselves are food safe. The other thing to be aware of is for an FDM printer, the fine seams can trap food and can be very hard to clean and can also be an issue in food safety. So you can print food safety, but you need to be careful about the process, the material, and the cleaning. And so these are good, 3 good references to it. You should start by assuming it's not food safe. If you do all of these things, you can then improve it. Then service bureaus. The Prusa runs an amazing collection. And if you come to Fab 25, we'll visit Prusa. This is somebody visiting Prusa to go see, this is their print farm. So any one of these printers is slow, but they have hundreds of them, and hundreds of them together is fast. And so these are busy cranking out Prusa parts. And so in my lab, I found a huge change. When you go from roughly 1 to 10 printers, they get used differently. Once you have a farm of that many printers, you use them to make more things and more interesting things than you do if there's only 1 or 2. And with printers down to a few $100s, for a few $1,000s, you can afford to set up your own print farm. I strongly recommend. Then Shapeways we saw went bankrupt. They've come back. They're a service bureau that has every kind of printer. Then the PCB houses that we'll see next week, no, in a couple weeks for PCBs now also all offer 3D printing. And so it's great to have the printer in-house for quick turn. When you want to do larger jobs, these are service bureaus you can send out to. Okay, so next you need to pick the printer and pick the material. Then we need to send a job to it. So far and away, the most common format is STL, and STL is both great and terrible. STL came from 3D systems. It was just a file format. It wasn't meant to be a standard. And it's nothing more than a list of triangles. There can be ASCII STL that's human readable. However, almost always it's binary because these files can be very large. You can get up to gigabit STLs. Binary ones pack it more efficiently, and it's just a list of triangles. So first, for this week's class, we want your design files. You don't, unless they're small, you don't need to check in the STLs because those can be large. And one of the things to note is if you like programming, it's very, very easy to make your own STLs. You can write algorithms that just simply write STLs if you want to describe geometry that way. One issue with STL, bizarrely, is it doesn't have units. It doesn't know millimeters or inches. So you have to make sure you and the printer agree on the units you're using. And then another big limitation is it has an attribute field that doesn't really get used. It doesn't know how to describe materials. So Ply was an attempt to add color to 3D printing. It's not widely used. AMF and 3MF is settling. These have taken forever. This was an industry process to come up with a successor to STL. And the problem is it's not a standard. It's sort of a shoebox of every standard anybody can think of. So these are settling, and they let you describe parts in more ways, but it's still been evolving. OBJ is the note about 3MF used in Bamboo Labs. OBJ came from Autodesk for computer graphics, but it's a convenient way to describe color and is commonly supported by color 3D printers. DXF is terrible in 3D. Again, I've complained about DXF. It came from Autodesk. It's not a standard. Autodesk is DXF is internally inconsistent. You can describe something in multiple different ways, and have all kinds of crazy results. So I would stay away from DXF. These are formats for computer graphic interchange that are beginning to get supported. Step, there's a note about Prusa Slicer. Step is a standard interchange format, and that's beginning to get supported. So STL always works, but it's triangles. You lose a continue. It's like pixels versus curves. You lose information when you turn it into triangles. AMF, 3MF, OBJ knows how to handle continuous geometries. Then voxels are where you describe an object as like pixels in 3D. And it's increasingly used in computer graphics. But what's emerging is printers knowing how to take voxels. So for example, for the polyjet process from Stratasys, where you can do individual droplets, for an object like this, it would be miserable to do as triangles. That one is much more easily described actually as individual voxels. Jacob, AMF, what's good is it can handle anything. It can handle FREPs, it can handle splines. What's bad about AMF is it's a container that can plug in lots of different descriptions, and they're evolving and they're not all supported. So AMF isn't a format, it's sort of a package of formats. So yeah, back to voxel print. For more advanced printers, it's a more interesting way to send jobs to it. Then most, and in particular, open or open-derived printers use G-codes. G-code is this ancient format. It doesn't make sense anymore other than it's widely supported. It's just a series of codes, and you have to know what the code is compared to what the printer does. But it's so widely supported, there are all sorts of things you can do with it. So what you're looking at isn't an image, it's a picture of a 3D print. This is a really interesting process that takes an image and modulates thickness. And so these, believe it or not, are all 3D prints from images. One of the things you can do with G-codes is instead of printing in flat layers, which is most common, you can print in curving layers. So in the design rules I showed you, you saw the layers and the steps in the layers. Instead, you can curve the print head to make curving smooth surfaces. And so that's been emerging. Another thing you can do is, I described what you can't do with overhangs, but this is a real, what this one is doing is making overhangs by making arcs that let you go off into space. And then another kind of update is when you build a building, you offset bricks. And so rather than putting all the filaments in the same layer, by offsetting them like you're stacking bricks, you can also get much better structural properties. And those are migrating into the slicers. So next up is the software. So when you're 3D printing, you'll have all your CAD tools, you have all the printer tools. In between, you want to look at the interchange. So I use MeshLab, open source, cross-platform. These let you look at meshes, and then they let you do all sorts of optimization. You can fix holes, you can smooth them, you can reduce density. So you need one of these kinds of tools to look at your meshes. Then slicing is how you take your job and send it to the printer. For the FDM style printers, Prusa slicer is a common one as a fork. Cura is another common one. All of these have informed each other and forked from each other, and they're all pretty converged. So the most recent updates, like non-planar Panther arc overhands, aren't yet well supported, but all of these do a really good job of understanding your geometry, making smooth outside surfaces, filling the interiors, optimizing, understanding multi-material, giving you time, all of that. So typically your printer will come with a recommended one. The open source ones support many of them. Then for running it, print run is a nice open source interface to printers. And then Octoprint is a handy tool for running print farms. And so rather than having to go to each printer separately, this is designed to have this running on something like a little Raspberry Pi connected to each printer, and then you can send jobs across the print farm. Many of the machines descend from Clipper, which is an open source firmware for what's running in the printer. And then to share your work, these are all options for sharing 3D designs, sharing sharing designs to print, sharing again designs, and then this is just a model viewer you can use to embed in your site to embed 3D designs. Okay, so for next I'm going to talk about scanning, but for printing, I want you to test your design rules, and you could use my example files. Design and print an object, and then the key part of this week's assignment, don't make it too large. There's a question about the Prusa print farm. It's up in the page. If you go back through the class recording, you'll see where I showed it. A key part of this assignment is something you can't make subtractively. So it has to have nested parts, overhangs. Design a part with a geometry that you can't make with a milling machine. You can only make with the 3D printer is the design challenge. Now for scanning, 3D scanning is frustrating in general. So depending on the process, you typically get a cloud of points. You have to then fill it in, typically with triangles. When you do it, often there's holes in it. What's called watertight is there's holes in your scan. If you print it, parts are missing. And depending on your print process, also you want not just geometry, but you want texture. You want to see the color. All of that's a very strong function of the lighting in your scene, the background in your scene, and the surface of your scene. So one of the tools in my lab is this, that's a few $100,000 machine. And what it can do is this. This is a fly-through of the head of a housefly. So this does X-ray tomography that scans an object down to micron resolution in 3D. That's wonderful if you can afford it. That's a few $100,000. And then the engineer who led the Formlabs Fuse spent time in my lab, and then he went off and started LumaField, which is 3D lower cost CT 3D scanning. And instead of buying the machine, you rent scanning. So for a few $1,000s a month, you have the machine and you use it to do tomography. So that's kind of the gold standard, but very expensive. This is a tool that scans a probe and measures down to atom resolution. You can do scan probe, you don't have to go down to all the way atoms. That gives you the absolute geometry at very high resolution. It's slow and it's 2.5D. It's measuring height as a function of XY, not full 3D. This is a confocal microscope. What it does is it scans a light volume, and you can do 3D scanning for where the light hits your part. So that works down to micron resolution. It can also scan inside objects that are translucent, works in 3D. That's again a $100,000 tool. I have a project in my lab looking at making an open confocal. It's potentially a really interesting tool to add to Fab Labs in the future. Serial sections are where you slice the object away. And so this is an article on scanning brains where you need to understand the neuron wiring. But you can do this to 3D scan destructively, where you grind or machine and you take pictures and you can assemble them into a 3D scan. And in fact, Quentin, Quentin, who some of you know, did an example of that recently. I'll link. This is an approach where you use an opaque liquid. Historically, this is called a milk scanner. And so you pour an opaque liquid over the object and you take pictures and you watch the object disappear. And then you use that as a way to scan the object. This is easily neglected. This is a digitizer arm. And so it's not automatic. You take an object and you touch points and then you click a foot pedal or a pen. And this doesn't scan the whole object. It measures the dimensions that you want. And so, for example, when Frank Gehry designs a building by crumpling up a piece of paper to make a crazy looking building, in his studio, they don't simply 3D scan. They use this to measure the important parts of what he did. And so you can add value by selectively digitizing with a digitizing arm. Then photogrammetry, this is an article on it, is where you take a series of pictures. And so Meshroom is a program, and what you do with it is you feed it, you just take lots of pictures, feed it to it, and then it solves a very hard problem of figuring out what object fits all those pictures. And so here I did it with this little work vise, and I'm doing it on this carpet intentionally because the carpet gives it information that helps it orient it. And if you zoom in, you'll see it got most of it right, but it didn't get all of it. It did pretty good, but it didn't do a perfect job. So that one is just for pictures. Then what's happened is there have been lots and lots and lots of versions of these aimed at versions you can run on your phone. These keep evolving. So Polycam is one of the popular ones right now. I'll talk about distance scanning in a minute, these are getting merged with that. And so the phone apps are getting better to do the 3D scanning. And then Quentin, who I mentioned for his project, made a scanner for photogrammetry that does consistent lighting and moves the camera. So that's all photogrammetry. And so you can experiment with all of these different phone apps. Then speckle scanning is where you give it a random dot pattern. This is a patent on it. And then you look at how the dot pattern deforms. And so the Connect from Microsoft ran that way. And let's see, that looks like that's a broken link. I'll fix that. This is software to work with that. Laser scanning this is a $30,000 laser scanner. It aims laser beams, and if you look at where the laser beam hits, as an object goes further away, the position of the laser beam moves. So this has an array of lasers it aims, and it looks at where the laser hits. That's a $30,000 version. And then, oh, that's another FabScan. I'll fix the FabScan link. Then structured light is an approach where you use a projector to send a light pattern of lines, and you look at how the lines bend. And so this is a version a while ago I wrote where this is what's called a gray code pattern, which is a particular way to blink the lines. And then it takes a series of images of the bent lines and then it combines them to do 3D geometry. Stereo is where you have multiple cameras looking. And right now, my favorite low-cost scanner is this one, the Crealities Ferret. It has multiple cameras. It also has inertial measurement, so it measures how the scanner is moving. And let's see. So these are scans I did right out of the box when I first got it. So, this is a chair. This is me wearing a fleece. What this does is, let's see, go to yeah, so it's $358, and it does a surprisingly good job of using all of that to do scan integration. So to scan me, you can't do that in one scan. You're painting it, you're going around it, and it has to continuously take the scans in and merge them. And so the Leo I showed you does a great job for $30,000. The Ferret does a really good job for $300. Then LiDAR is where you measure the time for light to go out and come back. And I showed you the individual device that does that, the ST for the input devices. TI makes a family of LiDAR chips. And so these are chips that take an image, but each pixel is like a little radio receiver and measuring the time for light to come back. Intel also has versions of those, although they're selling that. And then these LiDAR scanners, what's somewhat frustrating about the chips is they keep getting sold and bought by different companies. And so Apple in particular has gone all in on this. And the most recent Apple phones have ranging cameras that give you absolute distance that significantly helps it. Then so the question about edge or window. So something like the 3D scanning on an Apple phone is doing sensor fusion. It's using the cameras plus the LiDAR together to interpret scenes. So then this is a picture of me and at the time my much younger son Eli visiting a light stage. This is the state of the art for Hollywood special effects. And what this is doing is it's lighting from every direction and recording images from every direction. So if you just look at my face right now, there's surface scattering from where my skin is. There's also subsurface scattering from the translucency. There's light coming, bouncing directly off of it from a lamp. There's diffuse light coming from the room. And to model all of that, you need what's called the BRDF, the scattering field from it. And so this is a really impressive project they did in a tabletop version. So what's happening here is shiny glasses are horrible to scan optically because the light bounces off. It'll confuse almost all of the scanners. What they're going to do is put the object in here. Then this is an addressable LED array. They're going to spin it around. They have an array of cameras here. And what they're doing is they're lighting it from all possible directions with what are called spherical harmonics. They get a series of images. They combine all of those images, and then they separate out what's called specular, difforce, normals, roughness. They get all the parts you need for 3D graphics. And then they get the geometry, but then they can completely re-render it. And so what they've done with that is actually yeah, let me take just a minute to show you something terrifying. if you'd like to be terrified. In the digital Emily, they did this with an actress. So here's Emily. Okay, so they've put Emily in the light stage. Here she is talking. Oh, let's see. Let me pause. Wait, let's go back.
We specialize in high quality is a markerless performance driven. Metrics is a markerless performance driven animation company. We specialize in high quality facial animation for video games and films. Metrics is a markerless performance driven animation company. We specialize in high quality facial animation for video games and films.
So in fact, that's not a person. That's a re-render. It's crossing what's called the uncanny valley. That's recreating a person photorealistically. And then finally, SLAM is rapidly evolving. SLAM is simultaneously localization and mapping, where you're continuously 3D scanning to do augmented reality. And increasingly, AR on phones uses everything I've been describing to do 3D scanning, not as a static thing, but as a dynamic thing, driven by augmented reality. So for 3D scanning, the assignment is just scan an object. Optionally print the object you scanned. That's optional. At a minimum, scan something. And so for inspiration, let me show you a few examples. Ling Dong did one of the best assignments on this class ever. Here he's printing something you can't make subtractively, obviously, and he was a really good coder. So there was no design tool. This web page is the design tool. This web page describes and contains the code he used to make this object. So that was one of the most impressive can't make subtractively. Michelle in Vogue had a lot of fun this week. She played with all sorts of materials you can print to make inflatable materials, color, deforming. It was a nice tour through interesting materials. This one was interesting because Julia was so struck by the infill patterns that she used the infills to make the finished object. She thought the infills was more beautiful than anything else. And so the infill pattern was what she printed. And this was the real milestone in the history of this class. For this assignment, Wald, who's going to be part of the recitation, asked a Midjourney to make a surreal teapot and a surreal vase. And then he developed a workflow to combine the images. That's the render. And then this was on the PolyJet Color 3D printer. He printed the surreal object. And this one was really interesting because the assignment was to design it. And the question was, did he do the assignment? Did he design it? Who designed it? It was a collaboration. And again, this is a render, and then this is actually the print, that this is not a render, and it's not a 2D image, it's a picture of the 3D object. That was a real tour de force for the class. So you undoubtedly have 3D printed. The goal this week is to really learn the design rules and more advanced types of printing. So learn design rules, print an object you can't make subtractively. You're going to be limited by print time, so don't make it too large, and then scan anything. So that's 3D scanning week, and then important recitation on Monday on AI. And then next week we'll be back to electronics, and you'll start designing your own circuit boards. And as always, Saturday open time for help with anything. Okay, happy printing. Bye-bye.
Tschüss.
Bye bye.
Tack för ikväll.
Adiós, hasta luego.
Bye.